This was the problem maker. This is what caused a lot of the trouble. This is a composite sample with Teflon discs in it, lined up, various diameters, various depths. This is the raster scanner scanning that part with old sensor technology. We haven't done it since we've enhanced our sensors, but this is with the very, very beginning sensor that we started with. It was very easy for it to pick out those different discs. As we get smaller, we lose the ability to discern it, and at extreme depth, we lose the ability to detect it. But we now know how to enhance that. And it's an interesting thing. When you're imaging an insulator, the depth of penetration of this type of sensor is not related to frequency so much as it's related to the diameter of the outside transmit coil. So in theory, if you have a very large OD transmit coil, you can image to extreme distances. And if you have the ability to tell how far that distance is by way of either frequency shift or other things. In my paper, I don't talk about it in here because my presentation would go way too long. I talk about these inflection points where the effects due to gap are zeroed out and the effects due to material change are zeroed out at different frequencies. But that's in the paper. It's on your little thumb drive that you got. Here, this is FOD from the backing paper on composite. So they just cut up various bits of the FOD, they put it into the, at different layers into the composite, and we can detect those using this system. Again, with our early sensor, we were able to do that. We have enhanced ability now. And this is just the different backing papers that happen to be on the composite. Yeah.
I'm just wondering, is this useful for anything? I mean, can you detect impurities in a material, or what's?
Well, my final two slides are the product we built. I'm talking about the science behind it, and it may seem like, well, what are you ever going to do with that? But we had a specific task in the beginning. It was to make an orbital inspection head, because I owned a company that made orbital welding machines. I wanted to be able to forego X-ray and inspect it with this technology. That was what I was focused on. Turns out I can do this other stuff too.
This is just the ease of sticking the glue paper particles in the back of the composite? Is that what this is?
No, it's in the layers of the composite. Because the idea here is they tear away the backing material, they leave some behind, they lay it up, they want to be able to find it. Okay. So it's not on the outside.
Okay.
This is a configuration that is on a piece of composite here where it's called a seal. I don't know why it's called a seal, but it's this V-shaped composite section laminated to a flat piece of composite. It had various flaws in it, areas of debonding where when they put it in the OS machine, everybody knows what OS is, right? I know it's a brand name by, I guess Northrop Grumman developed it, and it's basically an ultrasound machine that is on a big gantry, and you have a sensor that raster scans in front of this section of composite, and it shoots a column of water at the composite, and that becomes the coupling fluid, this traveling column of water going to the composite. And then they raster scan with that. And it works very well, but it takes forever, and you're shooting water everywhere. It's in a chain, big booth. But that's how they got these images here. But there's this area of poor bonding that they knew existed in the part, but OS did not seem to pick it out very well. And so I scanned it with the raster scanner, and we pick up those areas of poor bonding very easily. And we had things like other holes that were just artifacts that they induced into the part, as well as lead markers. We see all of that as well. 5 minutes? Uh-oh, okay. Impact on composite, we see that. Here is the orbital scanner that I was talking about. That's the product that we actually made with this. And we're able to find porosity. That's a pore in a CT scan. This is a tungsten inclusion, and our scan matches up quite nicely to that. And we even made
a CT scan on the person?
No, I'm sorry. That's on a tube. If you remember, I said early on that we were making these welds for satellites, rockets. The tube goes to an X-ray booth. That's the CT scan that comes out. And as you correlate it to our image. And then We even have this robotic scanner that we developed to image regulators for satellites. But that gives us also flexibility to image a number of things. And what we're pursuing now is imaging of composites primarily, because that seems to be where the big industries are heading. And if you can offer something that's handheld, and we're developing a handheld scanner right now, about twice the size of an iPhone with a screen on it, so that as you move across the composite, a real-time image appears on the screen. So that's what we're developing now. I'm glad I answered your questions as we went, because we don't have much time for questions. If you have any, go ahead and hit me now. Yes?
Well, what kind of occurs to me is that, if I understand right, you're scanning, you're using one frequency when you're scanning.
That's right.
Right? And that's the frequency you determine to be the optimum for maximizing your signal noise ratio.
Right.
Would it be, have you ever considered scanning at multiple frequencies at the same time to generate a multi, I guess you could call it a multicolor image or a multi-spectrum image of the thing? Would that be of any benefit to you, to give you more insight on not only where the cracks are, but also what kind of cracks are they, or what kind of material is buried inside the...
The interesting thing about that is, do you remember that slide I threw in where I varied the frequency and we got same output?
Mhm.
Frequency changes don't give us the same thing in this sensor as frequency changes do in eddy current. In other words, a frequency change very directly affects the depth that you can scan. It does not with this.
Well, okay, that would, if you change the frequency, then could you use that to determine how deep the material is buried and then get a three-dimensional plot?
We have phase lag the same as you would with an eddy current. For instance, we drive at a certain frequency. If you superimpose the output frequency, with an oscilloscope, you will see a phase lag relative to depth. The data that we already pull out is data rich. We can determine depth, we can determine composition, we can determine distance, all locked within that one signal output. And it's the best output because it's resonant. Does that answer?
Yes.
Okay.
You mentioned early on about measuring the presence of gases. Can you applications that you use that in?
No, I've just done it, where you have air and then you might have glass, and in the glass you could put nitrogen. You basically tear it with a sensor. You measure the glass empty with air. You measure the glass full with nitrogen, and then you see the difference in the different materials. So yes, you can. Yeah. I'm sitting right here.
Have you ever considered measuring a phase also of the signal from your coil? You would be able to measure both, essentially, eddy current and permeability
Right.
in the same measurement.
That's, yes, the phase lag.
Right.
Yes.
And so, yeah, you could get more information.
Yes, and phase lag is different than resonant frequency shift. Both occur at the same time and can be separated.
Right.
Yeah.
Okay. And one
sorry.
more thing. Have you considered that the effect is a capacitive coupling effect as you approach your
I knew there was going to be someone who's smart in here. Yeah, that and that's a possibility. However, the capacitive effect shouldn't, with glass and the presence of nitrogen behind glass, it shouldn't be the same capacitive effect. I'm not saying that it doesn't contribute, because my suspicion is it does, but the capacitive effect would be mostly for surface effect, skin effect. Right. And it would be at higher voltages. We image at remarkably low voltage, and so my suspicion is it has an effect, but it's minimal relative to permeability. And there was one.
You notice any effects of temperature change?
Oh yeah, we get thermal drift, just as you would expect out of any sort of resistance-based or coil-based measuring. But we have filter algorithms that take those out. We can take out drift pretty easily. So it's not a problem, but it's there. I think they're going to kick me out of here. So, and somebody is supposed to queue up behind me, so I should respect that. But, If you have questions back there, thank you.